Hello and welcome back. Let's talk about an interesting application of integrals, volume of rotation. So let's say we have lots of things that are circular in shape. Say I have this bottle of cologne. It's in the shape of a grenade. It's circular this way. I also have this marker that I use, circular, but there's a varying radius. I also have this African drum. This is an interesting one. Circular, I believe it is a djembe, maybe, I'm not sure. But these would be very complicated to try to figure out the volume of. So, let's use the African drum example. Now let's trace this thing in here. Get something like this, and boom, and like that. So, I've got this very interesting shape. Now, we probably won't actually calculate this one, but I'll use it as an example because it would be a very complicated function. But we can take this area here and revolve it about the x-axis. And we'll come around here, just like that. Come out of the board and into the board, and we'll eventually get the area of that. Volume, sorry. But how would we do this? Well, what we can do is we can take a very, very small section here, like we did when we calculated area, under this curve, with size dx. Now this would be our radius, of course, the height, which is f of x, right? And we could imagine, instead of breaking this down into little tiny rectangles and calculating the area, we can imagine that we're breaking it down into little pieces of paper, circle pieces of paper that vary based on the size of the function. So first let's derive an area function for each of these little tiny circles. What could that area function possibly be? Well, we know that the area of a circle is pi r squared. But in this case, our radius is f of x. So our area function is pi times f of x squared. Not too hard to calculate, depending on what function you have. Hopefully you have a polynomial, otherwise you're in trouble. But now we can use this simple trick. Volume equals the integral of area as a function of x with respect to x. Now, we'll understand this a bit better once we get into Calc 3 and such. But for now, you guys are just going to have to trust me. So we have our bounds a to b, otherwise this would be very hard to calculate. So first you would calculate area of x, or you could plug it right in, and what you would get is this, plug it into here, and we could also represent our volume formula as this. let's work out an easier example than this African drum. My example is the function y equals x squared. And let's revolve this around into a circle, almost making like a mountain shape or something. Or maybe if you had a 3D arrow, it would be like the pointing part of it. Maybe the tip of a pencil if you have a strange sharpener. But here we go. So our function, f of x, is x squared. A equals 0, b equals 2. These are just simple bounds of integration. Our area function is pi times x squared squared, which is x to the 4. So our volume is the integral from a to b, 0 to 2, of a of x, which is pi x to the 4, dx. Because we are timesing each one of these areas by our small value dx that I talked about and adding them all together, and that's what our integral does. So let's calculate. This is pi times, what's the integral of x to the 4? That's x to the 5 over 5, and we're evaluating from 0 to 2. So this is just pi over 5 times 2 to the 5, which gives us 32 pi over 5. And that is volumes of rotation. Thanks for watching. Hope to see you guys in the next video, where we will be doing even more fun stuff with integrals. And I hope you continue to watch the series, because I really find Calc 2 very fun if you can understand it. I hope these videos help you understand them even better. Thanks for watching.